Okay guys, I'm going to continue solving in this clip the third problem from the exam and the first part of the fourth problem. The third problem described in a linear program a boat company manufacturing rowboats and yachts, and it gave a formulation of the LP but had some parameters missing, gamma and beta. And the first question asks you to determine the values of the missing parameters gamma and beta. So I guess this problem was somewhat similar to one of the problems on the review that I provided, but really what you needed to understand, I guess, was that the decision variables in this problem, x1 and x2, were related to the number of yachts and the number of rowboats to produce. Okay, and the constraints of the problem, the primal problem, are related to the waterproofing shop and the paint shop. The first constraint, really this 1/3 right here, that 1/3 is derived from this 3. Okay, so specifically it says the waterproofing shop can process 3 yachts per day. So that's why the constraint says 1/3 x1 and then also plus something related to rowboats less than 1, where the capacity of the waterproofing shop is 1. So sorry to be long-winded, but this first constraint is related to the waterproofing shop. And then that means the second constraint is going to be related to the paint shop. Okay, so once you knew that, it would have been fairly easy to determine the values of the missing parameters. The waterproofing shop can do 3 yachts per day or 60 rowboats per day. So that would have meant that beta was 1/60. And then it says the paint shop could do 2 yachts per day or 40 rowboats per day. The 1/40 you already see, so that means the missing one, gamma, is 1/2. Okay, so that was the first part of it. The second part of this problem says, given this dual LP, give an economic interpretation of the dual problem, specifically the decision variables, the constraints, and the objective function. So a lot of people wrote paragraphs and other things, but really you could have just sort of lined them up and knocked them off. So we had y1 and y2, those were the decision variables. Those were decision variables. The interpretation is the price of the waterproofing and paint shops. Okay, actually specifically the price for daily, you could think of it for daily use, because our problem is defined in terms of the capacity of the paint shop and the waterproofing shop per day. Okay, so this is like the price for a day's use of the waterproofing or paint shops. Okay, the objective function for the dual is really to minimize, well, let me say the total price paid for the boat company's resources. And again, to be explicit, that means a per day price for these resources. Okay, and then the other thing I asked you to address were the constraints. Okay, and again, the idea of the constraints is that they constrain the prices offered for these waterproofing and paint shops to be at least some amount, and those constraints are related to the amount of resources required to produce a yacht and a boat. So I would have said that the constraints constrain the value of a bundle of resources which could be used to produce a yacht or a rowboat. Constrain the value of the bundle of resources which could be used to produce a yacht or a rowboat to be at least the value of the respective product. Okay, and again, what we basically said is this, that here's our dual. Let's look at this first constraint. What this says is that the boat company could essentially use 1/3 of a day of the waterproofing shop and gamma of a day of the paint shop to produce a yacht. So the paint shop is not going to give up those amount of resources for anything less than $10,000, which is what we said the boat company could sell or profit off a yacht if it used these resources to produce a yacht. So those were the constraints. Okay, now I'm going to move on to the fourth problem. Just flip it over here. The fourth problem first gave an LP here, you see the top. Then it gave quite a bit of information here about the optimal basis. Okay, and then we have several questions. The first one says we're interested in doing a sensitivity analysis on B1. In other words, the right-hand side of the first constraint. And it gives some information and asks us to draw a graph of Z star versus B1. Okay, so in other words, we want to draw a graph B1 here on the x-axis, Z star here on the y-axis. And again, I told you exactly what I wanted you to give me explicitly. First of all, the current values. So the current value of B1, just the right-hand side of the first constraint, is 20. You can see that by looking at the formulation. The current optimal value in B1 is 20. The current optimal value is given by C sub B, B inverse B. And you would have known that by understanding the optimal simplex tableau that we've been using in class quite a bit recently. So that would have been at 26.67, B1 is 20. That's our current solution. Okay. The next thing that you're asked to explicitly draw was the current slope. Okay. So the slope is here how the optimal value changes as we change a right-hand side coefficient. In class, we understood that to be the shadow price of that constraint. So in other words, the slope here, let me call it M, is going to be equal to the shadow price of the first constraint. Now, again, you could have done a lot of work to calculate that, or you could have known that shadow prices in an optimal tableau are given by, at least for a maximized problem, C sub B, B inverse. So these are the two shadow prices for the first and second constraint. So the slope of this function is going to be 1.167. Okay. Next thing we need to put on here, the range where the current slope remains constant. Okay, you could have done a lot of work, but this one explicitly told you that delta could be the range -5 to 10, and the current basis remain optimal. And where the current basis remains optimal, our shadow prices are constant. So in other words, from 20 to 5 below 20, all the way up to 10 above 20, so from 15 to 30, our slope is going to be constant. So I'm not drawing units on my y-axis, so it doesn't really matter, but you would have drawn something like this. So that slope is constant. And then the last thing says, how could the slope change outside that range? And you didn't necessarily need to give an exact answer here, but the basic idea is that as we decrease, our slope is going to increase. Okay? So in other words, as B1 decreases, the slope of this function has to increase, and as B1 increases, the slope of this function would decrease. So in other words, we have this concave looking function. And that was everything that you were asked to provide for the first part of this, and I'll address the last two parts in the next video.